Ours can change so much. So we start all every team is like they say more how or what you do that.
Okay, good morning everyone. Good morning. So, we have 2 more lectures left before the end of the semester. I just wanted to inquire if there is enough interest on Monday. I know that our class ends at 12:25, and I wanted to solve a problem on transient conduction, which will take a little longer than 12:25. I was wondering how many of you would be able to sit along. So, and you feel free to leave because I will be recording it as well. So if you have to catch it up on the recording, that's also completely fine. But I want to take Monday, I want to solve a problem on convection. I want to solve a problem on transient conduction. So it's a nice problem. I'm going to post the problem statement on Sunday night. So you can take a look at it and make a decision based on how long you want to stay. Okay, but I hope to wrap it up by around 12:45 maximum. So I won't be taking up much more than that. Alright, 15 minutes, 20 minutes more than the usual lecture time. So that will double up as an overall review of everything. Okay? Alright, so today's problem. Interesting one. Hopefully if we have time we'll do 2 problems today. So in this problem you have the air cooling of hot aluminum strips. Okay, this is typically done by making use of taking a hot strip of aluminum, you pass it through a conveyor belt or you pass it through rollers. There is ambient air and there is air cooling taking place due to convective heat transfer. So we are going to look at something that resembles that process. This is of course a caricature of the actual process. I should say that. So take this with a pinch of salt, but it's more or less in many ways very practical. So these are rollers. Let's call this as a left roller set, L. This is R, okay, and the total length from L to R is 5 meters. And so what happens is that, of course there will be rollers along the middle as well supporting it. I'm not showing the entire situation. But these are the strips. These are 5 millimeters in thickness. Which is the thickness, and they are aluminum strips. So initially, I start from the left roller, and they are fed into the rollers at some particular velocity rate. Okay, this is given to us as I think 20 meters per second. So these sheets themselves V of the aluminum sheets, this is the velocity of the sheets, they are passed through the rollers at a constant steady rate of 20 meters per second. And so they start off before reaching the leftmost roller at a temperature of 300 degrees Celsius, the top surface temperature. That's typically what we're looking at, right? So before reaching L, which is the left roller, the temperature at that end is 300 degrees Celsius. They're meant to pass at a rate of 20 meters per second. They encounter room ambient air, T infinity. Okay, T infinity is given to us as 20 degrees Celsius. So this is in some many ways an inverse problem, right? Typically you have the hot plate, you blow air past it. In this situation, you have the air which is more or less still, but you are passing the plate through. This is still forced convection because there is a relative velocity between the air and the plate. Okay, so we are still looking at that situation. The following is the problem, the basic premise of the problem. Okay, I take all this loan and then I set up these rollers for the process of cooling these strips of aluminum. My hope is when they come to the rightmost end of the strips, their temperature should have dropped. Otherwise, what's the point of all this damn thing, right? So the idea is, okay, what is the temperature at the end of the rightmost roller? That is what we need to find out. So find, and we are given a lot of other information as well, which I'm going to write down. So find the T at, let's call this as X, the variable. X is equal to 5 meters. Okay. Here is the information that's given to us. So we have this thickness, I'm sorry, is actually 2 millimeters. Apologies. Velocity is given to us. So for the aluminum, strip, V aluminum 20. Then the density of aluminum is 2,770 kg per meter cube. The specific heat for aluminum is 983 joules per kilogram Kelvin. Okay. Then I have for air, I have the kinematic viscosity, which is nu. This is approximately 2.6 times 10 to the power minus 5 meters square per second. You're told that the Prandtl number is 0.69. Okay, and then you're told that Kf, the thermal conductivity of air, is 0.02 or 0.0338 watts per meter Kelvin. You're told that this whole problem, and perhaps this is by design, but the whole problem is performed under a transition regime of the flow conditions. Okay, so the Reynolds number is between 5 times 10 to the power 5 and 300 times 10 to the power 5. So this is transition flow. So that you're boxed between the laminar and the turbulent regions, and so the Nusselt number is given as the following: NUX. This is the local Nusselt number. Well, you're given the average Nusselt number, NUL, is 0.037 REL to the power 4/5 minus 871 PR to the power 1/3. And let me tell you, even though we are looking at flat plate problems, you take any type of external flow, flow past a cylinder. Okay, you're going to have probably a sufficient wake region and so on. But the idea is the same. If I am given the local or the average Nusselt number, I can calculate the heat convective flux rate. Okay, even if it is internal flow, makes no difference to us. The transition from laminar to turbulent is different in internal flow. The way you calculate the Reynolds number is different. You've got to take the hydraulic diameter into account and so on. But the idea is exactly the same. I know this creature from experiments. That's all I need. Okay? Alright, so that's given to us, and I believe that's all the information we need. A Prandtl number is given to us. I think I already wrote it down. Now, you're asked to consider a couple of situations. In the first situation, and the first situation, we are going to say that, and before I say that, this is all insulated. So the bottom and the sides are all insulated. It's not a big deal, it is just for the sake of convenience if we're assuming it this way. In the first situation, the top of the strip open to large surroundings. Whose emissivity is, and emissivity of the strips is 0.2. Okay, this is for the aluminum strip. This is open to large surroundings. Okay. Second situation, if this entire strip is enclosed within a room of finite dimensions, enclosed within a room of finite dimensions, third situation is we ignore radiation now. Which is a huge luxury. We should be thankful for that. And you're asked to consider the following as well. Because of the fact that the plate is moving at a certain rate, and because of the fact that the plate starts off at a high temperature, much more than the ambient temperature, there is going to be some advection of the plate. Okay, there is going to be advection heat transfer, which is the change in the energy of the plate due to the mass flow rate of the plate. Okay, which is as a consequence of its velocity. So you're going to consider the following. So draw a fixed control volume at some location x along the length of the plate or along the strip or along the journey of the strip. Essentially, it's like you have a window and then you have this strip passing through that window, which is the Eulerian perspective of fluid motion, right? So that's what we are looking at here. Consider advection of the strip along with convection plus radiation. You're asked to perform an energy balance. And obtain a differential equation for the temperature. And obtain an equation relating the temperature at any point along the length of the plate Okay, you relate this to the problem parameters. And in many ways, this is the crux of mechanical engineering, right? I mean, you take system dynamics, for example, is the seminal course for mechanical engineering. What you do there is you develop models of system behavior, and then you learn the tools to solve them, Laplace transforms and frequency response systems and so on. You're doing exactly the same thing here. You're developing system models based upon certain foundational principles, energy balance and mass conservation, momentum conservation and so on. And then you're using certain tools at your disposal, solving the differential equations and so on. And there is no difference between one versus the other. It is just that the fundamental equations that come up with the model are slightly different. The basic idea remains the same. this is an excellent problem for an exam where you have pretty much everything in the mix except for conduction, so maybe conduction is something one can throw in as well at some point. Alright. So let's do this step by step. We have some good amount of work to do. So first thing is, and I will be happy to answer questions maybe towards the end of the lecture. If you have any, please save them. I want to complete this problem fully so that we go over all the basics of it. Start off by looking at a control volume. Okay, so this is a control volume. I'm drawing the strip as well. Okay, so this is along the length of the strip. This is at some location X. The length of the control volume being equal to dx. Okay, so this is the left end of the strip, the right end of the strip at some location X. Here is my control volume. So the basic idea is, of course, the strip is not there yet. We have this window. The strip is going to enter the window at some finite time t and then leave the window at some time t plus dt. And as it enters and as it leaves, there is going to be a certain amount of energy transfer due to its velocity, which is what we call as the advection. This is on top of something else that is already going on between the plate and the surroundings. Okay, so here is advection in. And then this is advection out. The base of the plate is insulated, so there is no heat transfer between the base and the surroundings. But the top of the plate is open to ambient atmosphere, so there is going to be convective heat transfer between the top surface of the plate and the ambient, and that's at a local location, so I'm going to call it as dq, convection. There's also radiative heat transfer, so there's q radiation, or if you would like dq radiation. Okay? And we know that radiative heat transfer, if the temperature is constant along the length of the plate, is going to be constant, but here the temperature is changing at every instant in time along the length of the plate, so this is also dq radiation. Does this make sense to everybody? There is energy flow coming in, which is taken care of by the fact that the strip has a certain mass flow rate, so this is entering in. The strip is going to leave the control volume after a certain point in time, and then there is going to be, as it passes through the control volume, there is energy transfer due to convection and due to radiation. Okay? So these are all the quantities that are involved, and now let us write everything down. If you have this, you're pretty much done with the problem. The rest is just details, okay, which anybody can do. So advection in. You see, there is advection for the fluid as well. The fluid which is sitting on top of the plate. There is conduction for the fluid as well, but that is all taken into account when you look at the convective heat transfer between the plate and the hot surface. What we are doing here, and what I'm calling advection here, is the energy transfer into the control volume as a consequence of the flow of the plate into the control volume, or as a consequence of the strip coming into the control volume and leaving the control volume. Okay? So there's a difference. The equations remain the same. Mass flow rate of aluminum times the specific heat. You recall we obtained the energy equation where we used energy transfer due to mass transfer, energy transfer due to heat transfer. The energy transfer due to heat transfer and all those things are taken into account in dq convection. We're not going to do this again. This is just due to the mass flow of the plate. And this is E aluminum, specific energy of the aluminum strip. Advection out is just the variation of this one. So let's call this as delta x for convenience. You can call all of these as delta q and so on. It does not really matter, but you can leave it as dq if you would like. delta x, some finite region of the strip. So advection out is m dot times whatever it is coming in with plus some change in that. It's going to be the mass flow rate is a constant because you're told that the strip has the same velocity as it travels along the rollers. So m dot al does not change. So this is advection out. dq convection, dq radiation, or delta q convection, delta q radiation. So delta q convection, this is going to be the local heat transfer coefficient. Be very careful. So this is little h times T minus T infinity, where T is the temperature of the strip at any location x. So T is some x. Let us say that this is all done for a unit thickness basis. So the thickness here is 1 millimeter or whatever you want to think of. Okay, so this is just the area, which is delta x times 1 or on a unit length thickness basis. Okay. So that's delta q convection, delta q radiation. That's the big problem. You have to consider it 3 times. Okay, so let's do that one by one. So case A. Case A is if the strip is exposed to very large surroundings, then in this case, what is your radiation heat transfer equation? This essentially boils down to what we used at the beginning of the semester. Okay? So in this case, there is no thinking involved. Sigma T to the power 4, T surrounding to the power 4, assuming T surrounding to be the same as T infinity, that is completely fine, multiplied by the area exposed to radiation. That's Q radiation A. And the Q radiation for case B which I want to look at this fairly separately. So here is the situation. Okay, so here is the strip. This is surrounded by a large, fairly large or small or finite room. Okay, let's just call it a surrounding. Temperature is T surrounding. Temperature of the top of the strip is T at some location x. Okay, we are looking at it over length delta x. Because it is finite, I have to consider the idea of view factors. So in this case, if I call this as the strip S, and this is the surrounding, it is quite obvious to notice that the view factor for the strip looking at itself is 0. So F S S is 0. There are only two things communicating here. So F S S, F S surrounding put together is equal to 1. This is the summation rule. F S S is 0, so I have F surrounding is equal to 1. So this is the view factor. Obviously, I know the area of the strip delta x times 1, so this is delta x. And how to find delta Q radiation is by drawing the resistor network. So in this case, we start off with the fundamental nodes, which is the temperature of the surrounding and then the temperature of the strip. So here is E, B at T. T surrounding, this is the emissive power of the ideal body, which is at the same temperature as T and T surrounding. Then I have the radiosities, J surface, J surrounding, join them all together by the resistances. Here is one. Between EB and J there is always going to be the surface resistance, so we will call this as RS. Between E and J there is the surface resistance R surrounding, and then between the two there is the geometric resistance RS SUR. Does this make sense to everybody? Okay, this is the fundamental idea that we always use for a two surface enclosure. And flowing through all of these is your good friend delta Q, radiation. Okay, it's big. And if I have to list all the resistances, Rs is 1 minus epsilon s times A suffix s. Then R surrounding is 1 minus epsilon surrounding, A surrounding. And then the last one is the geometric resistance, Rs surrounding is 1 by area of the surface, view factors. Of course, I forgot to give you epsilon surrounding, but we can assume it's some kind of a value. Okay, so all of these will be given, and once I have everything, then here is the equation. T surrounding, those are the things that I'm interested in. So this is sigma T to the power 4 divided by R total, right? This is nothing but a set of resistors in series. So this is R total, Rs, R surrounding, so this is for very large surroundings, the first one. This is for finite surroundings. And obviously the good news is in the last case you just neglect all of these fellows. So delta Q radiation last case, C, which is 0. And before I proceed, I want to write the energy balance here. There is no E dot generated and so on. This is all done at steady state, so E dot stored is also 0. So whatever comes in has to be equal to whatever goes out. Right? So I have advection in. Is delta Q. Convection. Now do I know these arrows to be in this direction? I absolutely have no clue. This is an approximation or an assumption. Not an approximation, it's an assumption. If I'm wrong, that's completely fine. Okay? Delta Q radiation plus advection out. So this is energy balance. All right. Any questions so far? Yes, yes.
In the B equation, is there supposed to be a delta x on the numerator or no delta x?
Nothing here, no.
Nothing here.
No, because you see when you're calculating the resistances, you're already looking at the area, right?
Okay.
They're always inclusive of it.
I see.
All right. If you're looking at the flux, yes, of course, you have to divide through by the area, but we're not. Okay. Any other questions before I proceed next? This is the fundamental idea. If you get this far, the rest of the problems is just pure details. Okay? Plugging in, and then that is the boring part, but that's where most of the mistakes are made. So let's continue. some interesting things happen. I'm going to shift this board up. I want to remember the equations. I hope you have it written down. So from the energy balance, I have the following. M dot aluminum times E aluminum. This is advection in delta Q convection. Delta Q radiation plus M dot aluminum E aluminum, which is the advection out, plus the change in the advection. Obviously the terms on the left and the right, these guys are gone. I will rearrange everything, bring the M dot AL onto this side of the deltas. So minus M dot AL, delta E, AL is delta Q, convection, delta Q radiation. I'm going to keep delta Q radiation as it is, okay, because we have to substitute 3 different cases. When I reach the end point, we will make all these substitutions happen. Okay. So delta EAL, so E by definition is the specific internal energy. So this is the internal energy divided by the mass. So this is essentially going to be C times the local temperature minus some reference temperature. Okay. C is the specific heat of aluminum, which is given to us, 983 joules per kg Kelvin. So delta EAL is just going to be C times AL times delta T. Okay, that reference temperature is essentially gone. Or if you want, you can think of taking this equation here and differentiating it on both sides with respect to some variable dx, for example. If you do that, this is a constant reference temperature. It has no bearing on any of our calculations. Okay? At standard temperature and pressure and all these things that you would have seen in thermodynamics. So if I now take all of these, plug them back in, I have the following. M dot mass flow rate is density times the area times the velocity. This is exactly how you do it for a fluid flow. Okay? Area of the aluminum strip. With your permission, I'm just going to scoot this down a little bit. Okay? And I'll pull it back up. Area of the control volume is what I'm talking about. Okay? So that's essentially going to be delta T. This is the aluminum strip, delta T. Whatever the area that is available for advection in and advection out. So that's going to be this height multiplied by the width here. Okay, so I call that height as T. The area I'm looking at is this area that the mass is flowing through. Okay, so essentially that's the area I'm looking at out of the page. So I'm going to scoot this page up, or board up. And so I have, at the end of the day, let's look at case A. And then I'll say that case B is very similar and move on from there to case C, which is the more interesting of the 3. So I have minus rho, then area, which is T times 1, then velocity given to us 20 meters per second. That's m dot. Delta EAL is CAL. Delta T. This is equal to delta Q convection, which is H T minus T infinity delta X times 1. This was the area. Then I have Q radiation, delta Q radiation from the first part. So this is plus sigma epsilon T to the power 4, surrounding to the power 4, delta x times 1. Okay. Divide through by delta x. So that I have all of these put together, I'm going to call it as one big constant C. One can calculate that value. They're given all of those characters. Just plug and check. Okay, so this is not any interesting stuff here. So I have C delta T by delta x is equal to h, which is a local heat transfer coefficient, h times T minus T infinity plus sigma epsilon P surrounding to the power 4. Or if I let delta x go to 0, in the limit of delta x going to 0, this just becomes dt by dx. Everything else remains the same. Okay? So I'm just going to erase it and write it right away here. So this is now going to be dt by dx in the limit delta x tending to 0. Obviously, one cannot solve this problem because it's non-linear. You can solve it numerically. Same thing for case B. Okay, so there's not much to be discussed in that. So similarly, for case B, I'm just going to substitute Q radiation from case B. I will have everything else similar to that. Let me erase this. And so I'm going to have C delta T is h times T minus T infinity times delta x plus sigma divided by R total. Where R total is all of these put together. So R total is essentially 1 by A 1 minus epsilon of S by epsilon S 1 by F S surrounding, and here is what we make an assumption of. We're going to say that the surface area of the room is the same as the surface area of the aluminum strip that it is communicating with. Okay? So we're going to assume is equal to A, which is delta x multiplied by 1. This is an assumption. If you don't want to do it, this is also completely fine. It will just be a little more non-linear. Okay, this is not like it's any less non-linear. Throw all of this into the mix. So C delta T, because the resistance total is in the denominator, the area is going to now be in the numerator. So I can still do it this way. Is h T minus T infinity sigma all of this divided by surrounding. I left this unset here. One plus epsilon surrounding. So the only difference is that this is going to be a value greater than 1. That was not the case in this particular situation when you had the large surrounding. Other than that, everything else is pretty much the same thing. Nothing has drastically changed in the nature of the problem itself. Okay, and so this is still dt by dx in the limit of delta x going to 0. So non-linear. Does this make sense to everybody? What are the steps in the problem? Energy balance. Do the energy balance carefully. Then consider radiation carefully. Large surroundings, you go back to the introductory part of heat transfer. That was a good part of heat transfer. Everybody was thankful. And then slowly, you lose energy because you're doing energy balance all the time. And then you come to resistance networks. Okay? Alright. Now comes the good part. Get rid of radiation. Let's see what happens. Part C of the problem. So you go ahead here and then strike off that sigma epsilon t to the power 4, t surrounding to the power 4. So I end up with a very nice expression. H times t minus t infinity. Okay, all of those constants are called as capital C. One can calculate these values, it's not a big deal. As delta x goes to 0, this becomes a differential. dt by dx. Be careful, the h is a local heat transfer coefficient which is a function of x. Okay? And so you just have to rearrange stuff and say, okay, this is C dt by t minus t infinity is h dx. Then you have to perform the integration. What we are doing here is the following. We are saying, okay, hey, this strip saw the leftmost roller at a temperature of 300 degrees Celsius. This guy is passing through all of this particular length. So the integration has to be on the left hand side between the starting temperature of 300 degrees Celsius as it sees the leftmost roller to the temperature of the rightmost roller. And the integral on the right hand side is from 0 to L. So this is the model that we are going to be working with. Okay, so bear with me for the next 10 more minutes. To calculate that integral, here is what we do. Okay, so remember, recall first of all that h bar, which is the bulk heat transfer coefficient, this is the bulk heat transfer coefficient, h is the local heat transfer coefficient. Also recall the bulk Nusselt number or the average Nusselt number is h bar times L by Kf. So you see from the first equation, integral 0 to L h dx is h bar times L. You see why we are bringing the bulk Nusselt number is because that's what we've been given. Look at the top panel there, transition flow. And from here I see that h bar is NuL Kf by L. So which means this integral is actually something that is a piece of cake. You don't even need to do the integration. So if I look at this now, integral 0 to L h dx is just h bar, which is NuL Kf by L multiplied by L. The L and the L cancel off. And so integral h bar h dx is just the substitution. So this is Kf times all of that stuff, 0.037 or E L to the power 4/5, 871. And calculation of these empirical coefficients is lifetime work for a lot of people. So these are not something that people came up with very simply. Takes a lot of effort to get this. And the seminal nature of this is every problem that has transition flow will have to use that equation. Okay? So that's the powerfulness of these things. Alright, so we're done almost. I just have to substitute this back there. So integral constant, I'm going to call this as TL, which is 300 degrees Celsius, so dr dt by t minus t infinity is Kf times 0.037 REL 4/5 ER to the power 1 by 3. REL is using the total length of the plate to calculate the Reynolds number. So this is just U infinity times L by nu. This is going to give me a logarithmic solution. And I had, I think, a negative sign for the character capital C, if you recall. So all put together, this is what you'll end up getting. I have it somewhere. So eventually, substituting back, I think was minus rho V AL AL T times, and I think C AL. This is what you end up getting. Okay, so this is a logarithm. T right minus T infinity by T left minus T infinity. This is going to be minus Kf by rho VAL CAL little t, which is the thickness of the strip, 2 millimeters, and then the 0.037 times PR to the power 1 by 2. Substitute. TL was 300 degrees Celsius. This was 20 degrees Celsius. Be careful, if I told you that radiation was a part of the mixture, what should you do for your temperatures? You should put them in Kelvin. Please be careful. Here it does not make a huge difference because these are temperature differences, but you obviously will not be ending up with this kind of a neat solution if you brought in radiation into the mix. That's a nonlinear differential equation. You'll have to solve it numerically. ME 2850. Calculate TR. Ends up being 298 degrees Celsius. This is absolute disaster. I started at 300. I spent all this damn money. It's 298 degrees Celsius. This is atrocious design. Okay? So what should you do? Increase the velocity of the strip, so that your heat transfer coefficient increases. If the heat transfer coefficient increases, then your rate of heat transfer also increases. Convection heat transfer. Okay? So this is poor design. Now, with the last 5 minutes, we want to see if it is actually reasonable to neglect radiation at this point. I want to see if there are any questions before that. Of course, you can say radiation, the equations don't look good, so you can always neglect them. But is that a valid enough reason for us? Okay? That's something we've got to look at. I'm going to erase this panel here, okay? I'm going to consider only part A, okay? So can we neglect Q radiation? Look at this. Q radiation, by definition, okay, is, and this is for part A, large surrounding, sigma, epsilon, area, hollow frame. T to the power 4 minus T surrounding to the power 4, use some algebra, and this ends up being sigma epsilon Ts T square plus T surrounding square T